Let's use some of these integral formulas that we derived using the inverse hyperbolic tangent. Now, just to summarize, when we looked at the integral of du over a squared minus u squared, we were able to derive two formulas. The most important one was the one that utilized the inverse hyperbolic tangent logarithmic form. So we get 1 over 2a times the natural log of a plus u divided by a minus u in absolute value plus a constant. Now, of course, if we don't go to this form and we just utilize the inverse hyperbolic tangent, then we have 1 over a inverse hyperbolic tangent of u over a plus c, where basically we have replaced u with u over a. So there's some subtle differences here, but again, though we tend to like this for definite integrals, there may be some utility for this in certain instances, depending on the type of problem you're doing. So that's what I wanted to do with these two examples. Now, the first problem is this definite integral from -1 to 1 of dx over 25 minus 16x squared. Now, first thing you notice, this integrand is even, and you proved in one of your homework assignments that if we integrate an even function on a symmetric interval, we can rewrite it. That is, we can replace the lower limit with 0 and multiply the integral by 2. So to simplify. Now, again, what we want to do is make sure that we want to be able to use this formula so we can use this antiderivative. So we're going to write the 25 as 5 squared, and we're going to write the 16x squared as 4x quantity squared. So now we see that a is 5, and we see that u is 4x. So pretty good. The chain rule says we need a 4 dx. We only have a dx, so of course we put the 4 here and then pay for it with the 1/4. So this is table ready. This is ready to use this antiderivative. So we have the 1/2, which we were stuck with, and then we have the 1 over 2a, so we have 1 divided by 2 times 5. There, a is 5, right? And then we have the natural log of a plus u, 5 plus 4x, divided by 5 minus 4x in absolute value. Just application of this antiderivative, and we don't need the c because it's a definite integral. And then we evaluate from 0 to 1. So this is very simple to use this formula. And so when x is equal to 1, we get a 9 over a 1. And we have 9 over 1 here. That gives us a log of 9. And then, of course, when x is equal to 0, we just get ln of 5 over 5, or ln of 1, which is 0. So we end up with 1 over 20 times the natural log of 9. So again, this is a nice, user-friendly answer. We're comfortable with the natural log. You're actually comfortable with the inverse hyperbolic tangent, but when you're doing engineering problems, math problems, physics problems, it's sometimes very advantageous to have this when you've done a definite integral. Now, in the next problem, we're going to actually opt for this formula. So this is more of a engineering type physics problem. We're given that k is positive, it's a constant, and we're given that the acceleration dv dt is -32 plus k times v squared. And we're also given that v of 0, that is the velocity measured at time t equals 0, is also 0. And we want to solve for v of t. Now, what you might notice about this equation here is that instead of just having functions of t over here, we have functions of v, and that's something very different. So we have to get all the v's on one side, so we have to apply a little bit of algebra before we actually integrate. So what I'm going to do is to divide both sides by -32 plus kv squared to get this. So we have 1 over -32 plus kv squared dv dt equals 1. And now what I want to do is just multiply both sides by -1 so I can more likely fit this form. So that's going to give me a 1 over 32 minus kv squared equal to -1. Now, of course, I'm going to integrate with respect to t, so I'm just going to apply dt to both sides. dv dt is just dv, and then of course 1 times dt with the negative is -dt. So that's easy enough. Now, what we want to do is go ahead and apply the integration process. So first, what we see here is that the 32 can be written as the square root of 32 squared, and then the kv squared can be written as the square root of k times v quantity squared, so that we match up with this. But now, of course, just like with this problem, we don't have a square root of k dv, so we've got to put, by the chain rule, we've got to put the square root of k here and then pay for it. Now this is table ready. We can integrate with respect to t on both sides. So this is ready to go. That's easy. This is our formula, and I'm going to utilize this one. So now notice we have our 1 over square root of k, but a formula requires 1 over a, so we have 1 over the square root of 32, and then we have the inverse tangent of u over a, in this case, with the v. Now, the thing is that I went ahead and wrote the square root of k over the square root of 32 as 1 square root, and then multiply that by the v to make it look a little bit neater. And then, of course, the integral here is just negative t plus the arbitrary constant, where we just combine both constants of integration into one term. And now it's easy to get the constant value. That is, the inverse hyperbolic tangent of 0 is 0, and of course at 0 we get t equal to 0. So the constant is just 0. So that makes our life a lot easier. So now what we want to do is go ahead and solve for this v here. So first we're going to multiply both sides by the square root of k times the square root of 32. And so that's just going to give us a negative square root of 32 times k times t, as we have right here. And then what we want to do is to solve for v, so we're going to apply the hyperbolic tangent to both sides. The hyperbolic tangent here will absorb this, so this will give us the square root of k over 32 times v equals the hyperbolic tangent of negative square root 32 times k t here. But of course, the hyperbolic sign is odd and the hyperbolic cosine is even, so that makes the hyperbolic tangent odd, just like in regular trigonometry, so we can factor the negative. So all these little tidbits that we learn from regular trig are starting to apply to these hyperbolic functions. And so now we're good to go. What's left, we just need to invert this. And so if we invert this, we get v of t is the negative square root of 32 divided by k times the hyperbolic tangent of the square root of 32 times k t. Now again, you can at this point think about the actual definition of the hyperbolic tangent, but let's just see how this problem was actually made more convenient by using this form. So again, we wanted to solve for v of t, so we didn't want the v spread out into a formula. We wanted the v in one place. Here we have u over a, but here we have u in 2 places. So that would have required more work. If we go with this, we're ready to go, and we get a nice convenient formula. Now, of course, as you solve your problems, again, we look for patterns to be able to use either of these formulas. But if you notice in both of these cases, we clearly have this pattern. And so the problem will actually basically dictate which of these antiderivative forms you will need to use. So please take the time to look at this problem and pay attention to the details. This will be the types of calculations you will continue to do as you continue with your math courses. And we are done.